Good day, Mr. Daryl Hisola. Today, I will be discussing the supervised learning model that I have chosen, which is the interactive Intro to Dimensionality Reduction. The objectives of this project will be aiming to make students build, evaluate, and deploy a supervised learning model, either for classification or regression. With the help of dimensionality reduction techniques, the student will understand and show the application of these techniques to make the model perform better as well as efficient. Through the building of a functional prototype, learners will demonstrate how dimensionality reduction really applies practically in overcoming the high-dimensional data problems and also achieving higher computational efficiency. Further improves the interpretability of the model for machine learning. The project promotes learning by exploring their interactive activities to put concepts and tools presented in the reference materials into action, with the intent of being an all-inclusive understanding of dimensionality reduction as a critical component of modern data science workflows. For this project, I sourced the data from Kaggle's repository, leveraging high-dimensional data suited for both dimensionality reduction and supervised learning. The dataset used in the reference Kaggle notebook, Interactive Intro to Dimensionality Reduction, includes a variety of features conducive to dimensionality reduction techniques like PCA, TSNA, and UMAP. It shows the name, the source, and the description of the dataset. So why this dataset? High dimensionality. It offers 784 input features, making it ideal for exploring dimensionality reduction. Supervised learning. The target variable supports classification tasks. The applicability. Student can learn to visualize high-dimensional data and observe the impact of reduced dimensions on classification accuracy. The dataset workflow. Dimensionality reduction, applying PCA, TSNA, or UMAP to reduce the dimension for visualization. Model development. Use the reduced data to train classification models like logistic regression, SVM, or neural networks. Evaluation and deployment. Evaluate the model's performance with reduced features and integrate into an interactive prototype demonstrating the dimensionality reduction's benefits. The data pre-processing. The pre-processing steps include check for missing values in the dataset using df that is null, open and close parentheses, that sum, the data pre-processing. This includes checking for missing values, standardized pixel values, for consistent dimensionality reduction as shown in the Kaggle reference notebook. Verify and correct data types of features and labels to ensure proper algorithm compatibility. So the expected outcome of this pre-processing is a clean and pre-processed dataset ready for applying dimensionality reduction techniques and proper handling of null values, standardized numerical data, and encoded categorical variables to ensure efficient and meaningful feature extraction. Feature engineering. The first snippet of this code is a scale dataset where all features contribute equality to distance space and dimensionality reduction techniques. The second one is to enhance features that capture richer patterns and relationships, enabling better model performance and interpretability. Next is the data analysis and visualization. First graph is the scatter plot or PCA result. This graph visualizes the dataset after dimensionality reduction to two principal components. Each point represents a sample, and colors indicate class labels, cluster or separate separability between classes can be observed. The next one is the histogram. Shows the distribution of values for feature 1, highlighting its spread and skewness. It helps identify the central tendency and variability of this feature. Last is the correlation heat map features. The heat map displays pairwise correlations between all features, providing insights into feature dependencies. High correlation near 1 or negative 1 suggests redundancy, which dimensionality reduction techniques like PCA can address. Model building. The implementation of this using the MNEST handwritten digits dataset. Apply dimensionality reduction like PCA to reduce to 10 or 20 dimensions. Second, train logistic regression, decision tree, and random forest model on the reduced data. Third, evaluate their performance using accuracy and classification reports to determine the best performing model. Showing is the expected outcome. Successfully trained and evaluated at least 3 machine learning algorithms using dimensionality reduced data. Identification of the most effective model based on evaluation metrics, and the insights into how dimensionality reduction impacts model performance. Next is the evaluation and visualization. First, snippet code is the cross-validation for model evaluation. Perform key-fold cross-validation to assess the consistency and reliability of model performance across different subsets of the dataset. Using metrics such as accuracy, precision, recall F1 score, and area under the ROC curve for evaluation. Next is the confusion matrix visualization. Creating a confusion matrices to visualize the true positives, true negatives, false positive, and false negatives for each class. Next is the ROC curves and AUC. Generate ROC curves to illustrate the trade-off between true positive rate and false positive rate at different thresholds, and calculate AUC to summarize the model's ability to distinguish between classes. Lastly is the decision boundary plot. Visualize decision boundaries for models like logistic regression or decision trees in a reduced feature space like PCA with 2 components.